So just to give a brief background on multi-core processors and why these are the future in terms of avionics applications. So really, semiconductor industry started moving to multi-core processors back in the early 2000s, and this is when we realized that basically simply scaling the clock frequency, making architectural improvements, like prefetching, more ALUs, etc., was really starting to run out of steam, and we weren't, quite able to, get to 2x the performance every 2 years, which is roughly, Moore's law. So multi-core, processors started coming on the market to address this performance requirements moving forward. You don't quite get 2x the performance when you, put 2x the number of cores in a single package. There are other architectural considerations that kind of impact that. So it's not quite the same as scaling the clock frequency, in single core processors, but overall this was a way to really scale the performance. NXP then at that time, Freescale, introduced our first dual core processor back in around 2005. This was, I believe, our MPC 8572. And then we've really introduced our first big multi-core processor, the P4080, with the 8 cores back in 2008. So these have been around for quite some time. So in terms of why, multi-core processors versus single-core, processors. So one, we talked about the scaling of performance and continuing to, kind of follow Moore's law in terms of doubling the performance roughly every 2 years. The other is really size, weight, area, and power. If you look at here, this is, kind of a very high-level example just to give you an idea. This is based on one of our single-core CPUs back, in the, era of PowerPC. I believe this is based on the MPC 8548. So this was a single core device that operated at about 1.3 gigahertz per CPU core. And with 4 devices, you were getting roughly about 100K DMIPS of performance. And with about 12.8 watts per processor, you're getting about 51 watts of power dissipation for 4 of those devices. And then you have, the actual, fit rate for those. It's around, just over 1,300 per device. So it's coming out to about, just over 5,000 in terms of the fit rate for the 4 processors. And then you obviously have the memory subsystem for each of those processors, and you've got power and fit rates associated with those. And then you've got to interconnect these processors. So we're showing a PCIe switch and the power dissipation, the fit rate for that. So you can see it's roughly about a 72 watts worth of power for those single core, kind of system solution. And a fit rate of, almost 6,000, 5,700 roughly there. You go to a multi-core processor, and this is showing the 8-core. I believe this is based on the P4080. So this is running at 1.5 gigahertz per core, giving you over 200, K DMIPS of performance. So 2x the performance of the, single core solution that I'm showing on the left-hand side here. And you have, since you've got a multi-core processor, you still need the memories here, but you don't need as much memory as you needed for the single core option, so you can get away with fewer devices here. So we're talking about 2 DIMMs, that's 4 watts, about 40 fit rate. So you've got a significant reduction in power, basically almost half the power, and almost kind of 100% increase in DMIPS, and also a significant reduction in the actual overall reliability in terms of fit rate as well. So significant advantages in terms of moving to multi-core processors. Okay, so that's the benefits. So what are some of the challenges that you have when you move to multi-core processors? So obviously, you can see from the actual picture here that you have in a single core environment, you have access to all the buses, all the interfaces. So you can actually probe those interfaces and you can see what's going on. You have separate, memory interfaces. You can probe those and see what's going on, in each case as well. Also, if one CPU is going to fail, the other one's going to continue to operate, as well. So you have some of that available. And so visibility, is a key, factor in the single core area. And when you go to a multi-core, all those interfaces, all those buses become internal. So now you have to have some different way to, get traceability into what's going on inside that multi-core chip. And, this is, where we provide capabilities in terms of trace, debug features. And also, in terms of specificity, right? When you go to multi-core processors, there's a lot of challenges to, solve problems around resource sharing, accelerators to make sure that you balance the workload across those multi-core CPU cores. So there's additional architectural enhancements that were basically going into the multi-core architectures. Whereas in the single-core era, typically it was mostly an instruction set, kind of differences. So you have, x86, PowerPC, ARM, etc. Those were kind of the options. But single-core processors, were very similar in terms of the capabilities that they provided in terms of interfaces and processing capabilities. So multi-cores, a lot more differences, from a hardware architectural perspective to solve additional multi-core related challenges. And this is, showing you some of those challenges and how to, take advantage of some of the resource sharing that's going on. So obviously from an architectural perspective, you have to pay, attention to coherency across these, shared resources, CPU cores. You have to make trade-offs in terms of bandwidth and latency when you're selecting interconnects and so on as well. And also from a software perspective, obviously it gets a lot more challenging as well. You had single core CPUs, very self-contained in terms of the applications and software you're running on there. Now you've got multiple cores with resources that are shared, accelerators that are there to kind of get around some of the inefficiencies of the architecture as well. So software becomes a lot more challenging, and it really needs to be able to take advantage of some of the parallelism to be able to optimize for performance. Pure symmetric multiprocessing doesn't really give you good performance. So you really need kind of hardware affinity, to go with either AMP or SMP, processing to get the best performance out of the architecture. And also you have the rise of the hypervisors, obviously, to kind of abstract some of the underlying hardware and make it easier to run applications and have the hypervisor manage some of that resource, sharing that's going on from a hardware perspective and kind of virtualize that for the software applications. So really from a multi-core perspective, there's a number of enhancements that had to be made to get around, some of these impact of the software inefficiencies. So, as you are basically running hypervisors, you're running other software to basically manage these conflicts within the device that's taking up CPU cycles that were, can't be used now for the real workload that you really have. So load balancers, to basically classify the traffic and spread the load across the CPU cores was the, initial, reaction. How do you, design your interrupt handlers and so on to make sure that you handle interrupts, for these multiple cores and where those need to be routed. Other accelerators in terms of memory management, buffer management, packet handling, those types of things. So significant number of enhancements were added, for I/O and memory and internal resource sharing to get around some of these architectural challenges that we had in multi-core processors. So this is just an example. So this, I believe actually this is the LX2160 based example. So it's an ARM-based multi-core processor from NXP. So here, this is our latest generation. So you can see some of the, advantages of, what we've done to help with conflicts and in terms of resource sharing. So now you have what we call in our documentation kind of isolation contexts. So you can basically have, different processes, different applications in their own kind of, virtual self-contained environment. And then you can basically have, on trust zone, OS running in a, protected memory area as well. And then you can basically determine what resources you want to share from an I/O perspective. So either they can be dedicated to a particular context, or they can be virtualized and share across multiple different contexts. And you have, hardware and software resources available to kind of manage that. There's also, the memory management unit to kind of allow you to partition the main memory area. So you have private memory for each of these contexts, and you can still have shared memory as well. That's used by the overall systems. So a lot of different, ways to, solve the problem. But this kind of gives you, how the device could be configured to get around some of these issues. So PCIe interface sharing, or dedicating some of those lanes per context basis, and also some of the wire rate kind of processing where the data is coming in through PCIe or Ethernet, basically doing some classification on that to make sure that you route the traffic to the appropriate context and hardware resources internally to do the actual processing. So the other area where we've done a significant amount of work is through our collaboration with the industry. So we formed this Multi-Core For Avionics working group just over a decade ago, I believe. And the intent was this is to help our customers really certify their systems based on multi-core processors. And we have a conference that we hold every year, once a year, but this is really just the advent of all the work that goes on during the rest of the year. We do a deep dive on a lot of the internal architectures of our multi-core processors and provide a lot of the collateral and information that's needed to certify the system that we don't typically publish in our standard documentation. So there's a lot of advantages to joining the the MCFA organization if you need access to that documentation. We create a lot of artifacts around the multi-core processors, but also around our design philosophy, design methodology, our process technology. So there's a lot of work that goes on behind the scenes. We have a steering committee that's formed from key industry players as well as NXP that basically prioritizes and works on these items to help the industry move forward from using multi-core processors. And the next event we're hosting in 2021 is probably going to be around end of October, beginning of November. So you'll see more information if you're members of that organization. So in terms of more details, what do we provide to MCFA members? So as I mentioned, we do a deep dive on the SoC architecture. This includes hardware enforcement in terms of how the resources are partitioned, if there's any kind of interference between different areas, how you can configure the device to prioritize what IP has access to those areas. In terms of fairness, worst case execution times. So, we work through those kinds of discussions, and obviously going through the details of our MMUs, IO-MMUs, interrupt routing, etc. So a lot of internal architectural information to help understand the behavior of the multi-core processor under different use cases. And also we discuss details about, debug visibility. We have also, additional cores, inside the multi-core processors that are used as part of some of the accelerators that we have. So we discuss details around those and any firmware that's used on those and what's needed to help certify systems. We go through all the kind of, error detection reporting, the reliability quality information in terms of the single, upset, error information, reliability data that's needed. And then really overall NXP and hardware and software development processes so that you can be assured in terms of, how do we, design these processors, how do we track quality and so on. And then process technology as well. So these are just some of the things that we do. And obviously we work with partners like Curtiss-Wright and also Rapita Systems to make sure they have access to all of this intel and information, to help them develop, their solutions for the industry as well. And I believe that's my last slide, so I'll hand back over to Nick.
Thank you very much, Altaf. That was very interesting. So I'll pass straight on to Gregory from Curtiss-Wright, who can take over from there.
Hello, so my name is Gregory Sikkens. I work with Curtiss-Wright. What I'll be talking to you about today is how do we bridge from, you got this terrific SoC solutions from NXP and data to support it, and how do you bridge that to your system? And that is basically through our COTS, or commercial off-the-shelf single board computer modules, but are really safety element out of context, so they're developed to meet DO-254 and so on. So let's get into it. So where we've come from up to 2014, it's been a traditional model where Curtiss-Wright would respond to customer requirements and develop hardware based on our existing IP to meet DO-254 and DO-178 at that time B requirements, and provide platform software as well for the single board computers. And in 2014, we established a commercial off-the-shelf, or a COTS product offering to meet the DO-254 requirements, and do that with basically a no NRE component. That is, the hardware and the DO-254 lifecycle data is off the shelf and doesn't require any NRE to customize. We started out with initially a P5020 single board computer. The number in brackets shows the number of cores that we support. So while that's a 2-core processor, it was a very conservative product where we only enabled 1 core. And we also had a companion product, an AMD 4690 based graphics module to work with that so that we could deal with basically processing as well as visualization in a safety certifiable environment. And then later on, we've moved to the T2080 single board computer where we support the 4 cores. So again, it's T2080, it says, it implies it's 8 cores, but with CAS32A, there's the no hyper-threading type of rule. So we limit it to 4 cores. So that's 4 pure cores, be 4 with hyper-threading. And then we also upgraded the graphics capability 8860, so more performance. And then we also added a avionics I/O module as well. And we've just announced earlier this year the LX2160A single board computer, which has the 16 full-on ARM cores. So how do we make these usable or easy to use in a system? And that is we follow industry standards. So basically the CMOS or SOSA, which provide common pinout so that our modules are interchangeable with other modules that you may find on the market. FACE, so future airborne compatibility environment. So this is more on the software side so that you've got compatible or aligned interfaces at the lower level. That is, you can port your application relatively easily from one system to another. VITA or VITA standards. So this is the form factor and the ruggedization of the modules. So we're 3U. It's a fairly common form factor in the defense aerospace market. And then also MIL standard from an environmental perspective, as well as DO160 from an environmental perspective. So they are designed and qualified for harsh environments. They include built-in test equipment, or you might also want to consider that as a safety monitor. So there's built-in hardware safety monitors so that you've got a high failure mode detection coverage. We provide a standard data kit, the basic DO254 lifecycle data, so a PHAC. We also provide the requirements so that it can trace to your system requirements. The top-level assembly drawings, HCCI, HCI, your hardware accomplishment summary, as well as a failure modes effects analysis data so that you can incorporate that up into your system safety analysis. And this is all done with the means of compliance, so the AMC 2152A, which is aligned between the EASA and the FAA, which calls up DO254, and it also adds additional objectives around custom devices, so that's your FPGAs, PLDs, COTS device selection, as well as the circuit board assembly itself. And these are all designed so it can be used in a system slot with DAL-A requirements. So how do we minimize your cost and risk? Well, we're involved with a number of key industry groups. So the DO254 users group, I think we have some members on today. Multi-Core For Avionics, so this is the NXP group that Altaf mentioned. The Society of Automotive Engineers, specifically the SAE Aerotech Conference. And then also the Safety Critical Systems Club, which is a UK-based group with which also has a subgroup working specifically on multi-core issues. And then we also perform all our developments with FAA DR oversight, and there's also a letter available from DR to substantiate that. And then we also provide the lifecycle data, as I mentioned. This AMC 2152A is the harmonized means of compliance between the FAA and EASA, and it covers the basically calls up DO254 and then additional guidance, as I mentioned, for custom devices, COTS devices, and circuit board assemblies. This essentially replaces, for the most part, the EASA cert memo and the CAS papers, except CAS32A for multi-core. There is a draft AMC out now to talk to that going through reviews, talk to that specific topic as well. It's more than just the DO-254 process, and it's more than just the additional objectives from the AMC. Or we also do a failure modes effects analysis. We do it at a functional level, and we also do it at a functional level for the complex COTS devices. So for a T2080, we do a failure modes effects analysis on it at a functional level, and then we roll that up to the card level at a functional level as well. Follows the best practices of the ARP 4761, and this is where we get our requirements for defining the built-in test software, as well as the built-in test equipment if we need additional hardware capabilities to meet the fault or the failure mode detection coverage. And we provide it in source form, so it can be tailored to the application's use of the functions, so that makes it easy to adapt it to your system and application need. From a multi-core certification perspective, putting the chip on a board doesn't really have an impact with respect to the CAS32A and the draft AMC 2193, but there's three key elements that essentially CAS32A looks to address. One is the device data. Is there sufficient data to understand the interference channels to address the objectives of CAS32A? You need the RTOS support in terms of, does the RTOS provide necessary execution metrics so that you can determine your usage of on the interface channels, and if you got any conflicts or if you're going to have any impacts to your worst case execution times. And then application testing. So you've made these assumptions or these models of what your worst case execution times are going to be, and then you need a tool like what we're talking about later on here today with the Rapita tool suite. You need the tools to prove out your models. So from a onboard, so for our board level design, we need to select a processor that has this support. And we do that with like T2080, where we got the Multi-Core For Avionics data package available from NXP, really through the MCFA group, where it's basically you have an NDA with NXP, you join this group, and you have access to the SharePoint site, and you can download the data packages for the supported processors. And that data goes beyond just the data you need for multi-core. It gives you the additional data to support its use in DO-254 hardware, as well as the objectives in the AMC 2152A, such as microcode, for example. So for example, here's a block diagram of the Curtiss-Wright T2080 SBC. As you can see, we don't really add any complexity or any additional interference channels to the mix. What we do is we take the T2080 SoC and connect it up to flash memory for program storage, SD-RAM for program execution, some other memories and functions such as lapse time counter. And then the rest of it is wiring up the I/O such that we present it to a connector that's available to the backplane in the system for general use. And that's about it. So what we do provide in terms of data in our manuals and also safety manual is what specific interfaces that we wire up to on the T2080 such that you can understand where your application data is coming into with respect to the coherency fabric and other interfaces within the T2080, so that you're basically taking the NXP data plus the data from Curtiss-Wright to model your application's use of the multi-core, and also look for conflicts and model your worst case execution time. And then you've got the foundation that the hardware was developed to DO-254. You've got the artifacts for that, so you got all the foundation work, and we're just moving it up to the system level to support that. So I think that's about it. So effectively, what it is, it's a safety element out of context. We've developed it to meet the safety guidance and means of compliance guidance, and provide data to support that, so that at a system level you can achieve certification. We also can provide units to help with development and demonstration, and also for testing. So this is a rugged benchtop system that's conduction cooled. It starts out with this I/O panel that has the commercial standard connectors to make it easy to get going in the lab very quickly. We can populate it with a T2080 single board computer and some graphics modules, and you can get an application going very quickly on this system. It uses an external power supply just to keep it compact for lab use, but it can actually grow into a fully deployed system. The power supply module can be added to the bottom, and this I/O panel can be replaced with one with 38999s, for example, to ease from development into deployed for just a quick step. And that brings me to the end of my part, so I'll return it to Nick. Thank you.
Thank you very much, Gregory. That's great. Now to move on to more of the software and verification side of multi-core analysis, I'll pass over to Stephen VanderLeest.
Hello, everyone. Thank you for joining us. I see a number of folks that I know on the attendee list and many more that I don't know. I am glad that you've joined us today. I hope you find the panel interesting. I see lots of questions showing up on the chat, so I hope we have time to cover many of those. They're very interesting, and hopefully we can tackle a number of them between the panelists. So my part is talking about thinking about the overall system, so not just the software, but the hardware underneath it. One of the questions I noticed was asking in terms of CERT, are we talking about hardware or software? From the CAS32A perspective, it is the entire system, and you do have to account for both. CAS32A is the current guidance. We're expecting AMC 2193 to be published really any time. It has already gone through a comment period, which ended earlier this year, and they were anticipating publishing it in Q2. So we're a little bit past that. As of yesterday, when I checked, it had not been published yet, but it really should be coming out in the next weeks and months. The draft that came out earlier was largely following what CAS32A had already stated. So first, a little bit about Rapita. We are a tools and services company. The Rapita Verification Suite covers a number of the needs that you would have for verifying software to a standard such as DO-178C, creating tests, doing structural coverage, doing a worst case timing analysis, looking at your task scheduling, and so forth. So one of the key advantages of the Rapita tool suite, it does measurements on target, and that will become particularly important when you're looking at CAS32A. But even on single core, doing measurements on target give you the most accurate view of the system performance. And then often customers will engage us with services as well. So sometimes we'll start out doing some of the V&V work with our tools, train the customer, and then you, the customer, take the tools and run from there. And so there can be a different flexibility in terms of how to get started. Especially for multi-core, we find that it's usually important that we are working collaboratively with you, the customer, to get started on this analysis, even if ultimately then you walk away with the tools and complete that analysis. But especially just setting up the overall framework of how to do this type of V&V is fairly complicated, and so usually customers will start with us on some services. We are located in the US and in the UK. I happen to be located in the US. I'm speaking to you from Grand Rapids, Michigan right now. All right, so you've heard a little bit of this, but let me just summarize. Both panelists touched on some of these aspects. So why have we not done multi-core before, and why is the aerospace industry now adopting multi-core? So for one, it's a complicated approach to use multi-core, as you've seen. It can result in what looks like non-deterministic behavior if you don't take various mitigation approaches. There wasn't clear guidance. CAS32A is not an advisory circular yet. It is about to become one. The expense of verifying such a system looked beyond what most companies wanted to take on, and there wasn't really a commercial solution available. But today we're seeing that there are performance improvements available for size, weight, and power, as Altaf had mentioned, that are driving customers now look at adding functionality and features to their systems through the power that they can get in multi-core, assuming you can take advantage of the additional power of those cores. Also, it's getting very difficult to actually find single core processors anymore. So in the last 10, 15 years, some avionics boxes have used multi-core processors, but simply deactivated all but one of them to run them in essentially a single core mode. Even then, you need to provide some assurance that those other cores truly cannot create interference, that they're being held in reset, or that they're running an idle loop that's not creating any activity, something along those lines. As I mentioned, there is guidance now. CAS32A has been out for a number of years and is about to become formalized. And now there is becoming clear a roadmap to certification, and including from folks like Rapita. One of the key things of doing this type of verification for a multi-core system is that you need an ecosystem, a collaboration of a number of partners. This panel attempts to represent a slice of that type of collaboration. So you need to be working with the chip manufacturer, someone like NXP that is creating multi-core processors and systems on a chip with the associated certification evidence. You need board suppliers like Curtiss-Wright that are selecting the right chips, putting them on the boards and configuring them in a way that you can get to certification and providing the evidence around the overall board. And then at the software level, so you have RTOS providers. There are a number of aerospace RTOS providers that understand CAS32A objectives, and then you need verification tools that work with that overall system, your applications, your RTOS, your underlying board and hardware. If you are looking at a integrated modular avionics IMA type system using, for example, ARINC 653 for partitioning, you may have multiple levels of suppliers providing software into partitions. Those all need to be considered when you're doing CAS32A objectives. There are a number of industry groups that both of these that you see here, the MCFA and the MCWG, are industry collaborations. The first one is hosted by NXP. The MCWG is across multiple industry partners. And there are some research projects. For example, Rapita participates in a funded project called MASTEX, which includes a number of different organizations working together on this problem of certifying multi-core systems. So from a customer point of view, how do you pull together these partners to get to a multi-core system that gives you the performance you need to provide your new features, your new functionality, and also get to assurance in a cost-effective way? So if you think about moving through these different ecosystem partners, you're going to start with a chip manufacturer that's providing a chip that has some mitigation mechanisms on board the chip. So you heard Altaf talking about the shared resources that are available to these cores, ensuring that they have equitable access, providing some means of partitioning that access on chip can often be quite important, and then providing evidence that can be used with your airworthiness authority. That then flows to the board supplier that selects that chip, builds the documentation for certification around that, documenting, for example, how they are using or deactivating certain features. Gregory mentioned the T2080 chip that they're using on one of their systems. They are thereby configuring and using some of the functionality of the T2080, but perhaps not other functionality. Where you can demonstrate that your configuration has deactivated a certain feature, then that's much easier and straightforward to say, well, then that feature cannot cause multi-core interference. The T2080 is a chip we've happened to have done work on several different projects. There are 40-some shared resources that you have to consider that the cores can all access on that particular chip. each of those shared resources has multiple modes of operation, or if you think of the CAS32A language, interference channels associated with them, anywhere from just a couple to a dozen different interference channels for a single shared resource. So if you're using every single feature of the T2080, you could have potentially hundreds of interference channels. On an actual practical system, you likely aren't using all of those features. And so on a particular board, it's going to narrow down quite far from that. We haven't seen any project where every single feature is being used on a particular system. Furthermore, once you get to the RTOS provider, you may narrow that down further. There may be features that, although the board is enabling it, the RTOS then simply disables that at boot up. So that then narrows down even further which interference channels could be operational during flight that you have to consider. The chip, the board, and the RTOS all may contribute to partitioning, to mitigation mechanisms that can bound and make that interference deterministic, so that when you're running multi-core, you actually get the performance. So if you have 4 cores, you're probably not going to get 4x performance, but you hope to get more than a single core performance. And we've seen that with proper mechanisms in place, you can get close to that. If you don't put proper mechanisms in place, you may not actually see a provable benefit. That is, your worst case timing might not be demonstrably better than the single core if you don't do your homework, if you don't configure and optimize the system properly. And then on the right here, we have certification partners like Rapita that work with you to provide that certification documentation, that you verified that your multi-core interference channels have indeed been mitigated, that you have deterministic performance that can be predicted for what you will see under worst case scenarios. And as I mentioned earlier, we provide tools and services to do this work. Okay, so I mentioned this earlier. The advisory circular is expected out at any time. This will harmonize advice from EASA and FAA so that there is the single advisory circular on both sides of the pond, which give us guidance on how to deal with systems where 2 or more cores are activated. So for now, you can look at that draft that's out and available. Largely looks like what CAS32A said, and we'll see what the published version is hopefully shortly. So some of the challenges that we look at when we have a verification project with multi-core fall along some of these lines. So this at least gives you a flavor of the sorts of analysis that needs to be done. First, just simply identifying what are the types of interference. I mentioned on a fairly high-end processor like the T2080, you can have dozens or even hundreds of potential interference sources. There are some direct types where we simply can look at the documentation that comes from these different partners and identify, here's a shared resource. For example, you can look at that documentation and see that there is a level of cache available to all the cores. It's usually the last level of cache. On the T2080, there's an L2 shared cache. And so that's directly visible in the documentation, and we can measure what that effect is when they all are attempting to use that same shared resource. There are indirect types of interference where you may see that because you are accessing, for example, a shared memory, you also are accessing a shared interconnect to get there. That may or may not be documented from the chip manufacturer. In most cases, you can at least get a hint of it, but you have to take that into account. And then there may even be sources of interference that are not obvious from any of the documentation. This is where measurement on target is really important, because you sometimes can see surprises where there's a type of interference that you maybe didn't expect and you need to explore further. The assumptions that go into this type of verification are multiple. For example, we typically are going to use onboard performance metrics, sometimes called a performance monitoring counter or a hardware event monitor, and those devices allow us to track and calibrate the level of interference to particular shared resources. Those PMCs sometimes have bugs. You'll see errata published for that what they're counting isn't exactly what you thought, and so they have to be checked and verified. So we want to trust those counters, but we need to verify them. you have these various mechanisms to provide partitioning. It might come from the chip, it might come at the board level, it might come at the RTOS level, and then we have to think about how do we verify and determine that those mechanisms are working. Partitioning is a general term for how that might go. You can think of ARINC 653 type partitions where you're running an application within a partition that should have spatial and temporal isolation from other partitions. That depends on mechanisms implemented in the RTOS, mechanisms that the RTOS is then managing within the hardware, and that all has to work together correctly. In terms of quantifying what that interference looks like, then we typically use our tools to gather high water mark type measurements from the timing data of your code running on the actual system, and from that then we can estimate what the worst case timing would be based on various worst case scenarios that we create. We use a hybrid approach, so we're analyzing the software to understand what it's doing from a source code level, and then using our timing measurements on target so that we can associate where the interference is happening, where you might see timing that is not optimal, and map that right into your source code to see what are we doing that's causing this unanticipated or perhaps even unacceptable interference. And so that leads me to this last point. Static analysis to come up with your worst case execution time estimate is insufficient. In fact, CAS 32A specifically calls out that you are going to need to do on target types of measurements for multi-core. You do need to do the static analysis as well, so it is a combination, but the actual on target measurement is important because we cannot completely model what's happening on the chip, the board, and the RTOS together from a static point of view. There are just some very difficult or even unavailable types of information that we capture through measurement that you might not be able to see through static or simulation types of analysis. Rapita provides services to think about this. It provides documents and processes to help jump into developing the certification package around CAS 32A. And in the middle there you see one of the key parts of our offering for multi-core is an interference generator that we call a RapiDemon. And the RapiDemon creates the worst case scenarios by actually intentionally creating interference to particular shared resources. So for example, we know that that shared level of cache could create interference. The RapiDemon runs on another core and intentionally creates traffic to the L2 cache. It's finely tuned and crafted to do this, and then we see what impact that has on the application on the, say, the first core. And then for each shared resource, we have a calibrated RapiDemon that creates that interference to provide the worst case scenarios that we can then measure what are the impacts on the application. In terms of a workflow then, I mentioned these different tools we have for testing, doing timing, and so forth. Those all come together with a multi-core project. So we run your software instrumented to get timing on the target, and then we run RapiDemons on other cores of the system to measure the impact. Typically, we'll run the application by itself on a core to get a baseline timing, and then start adding RapiDemons on the other available cores as adversaries to intentionally create the worst case scenario, measure the timing effects, and quantify whether interference has been appropriately mitigated. And this has to be done for each interference channel that you determine is active on the system. Hopefully, you've removed some by analysis that you can just say those are deactivated. Those aren't available. But for the ones that are available in operational flight, we use the RapiDemons then to test this. The RapiDemons aren't running during flight. This is during testing where we're using the other available cores to create that worst case scenario to measure each application. This is helpful for IMA, by the way, because you have a way then of doing your testing one application at a time, proving that the system is appropriately partitioned as you integrate it together. So especially if you have suppliers providing that IMA partitioning hosted application, information from different at different times from different perhaps suppliers, you can break down and incrementally work through how to provide the certification evidence and then accumulate it into an overall package. So if you are the a platform provider or and ultimately the certification applicant, you can accumulate and pull together all of that evidence overall. And so in each of those applications can use this particular workflow to provide their chapter of that overall document. The documentation can be fairly complex. We provide a set of templates, tests, process flows, and so forth to meet the CAS 32A objectives. There's 10 objectives stated in CAS 32A. If you look at, most of them are fairly complicated. They're complex, multi-part objectives. So those 10 actually expand into quite a few different tasks that need to have verification evidence associated with them. So this gives you an idea of how that all pulls together then. We do a platform characterization kind of on the left-hand side, a software characterization on the right-hand side, and this might be done multiple times if you have multiple applications. That all has to flow together into an overall package to show compliance with CAS 32A objectives. If you're familiar with tool qualification, the way, for example, how Rapita does, we have a generic qualification kit over on the far right-hand side there, but that then has to be shown to be correct on your particular system. So there's a part that you, the customer, do to take our tools and show that they are valid, that your results are valid on your particular system. So there's sort of a last part customization to say this is qualified on our system, and we've got the proof to show that that's the case. So if you're familiar with that flow, that's what's happening here, but now it includes these multi-core aspects, including this use of Rapidemons to create interference that we then measure as our worst case test. Okay, so to wrap up my part, just a couple main points. Assurance of multi-core is challenging. It's something that now today we can do. 10 years ago, the industry, we really weren't sure what to do. Best practices now are coming into place, and Rapita has now a commercial offering to walk you through assurance of multi-core systems according to CAS 32A, and soon Advisory Circular 20-193. It's key to have cooperation between all the partners that are providing the parts of the system. So you want collaboration and flow of information to build your certification package from your chip supplier, your board supplier, your RTOS, your software suppliers, and a company like Rapita to help you pull those all together into a cert package, providing the tools and the expertise to hit those objectives. Thank you. And I think I'll turn it over to Nick here. I believe we have a demo next.
Hi, yes, thank you very much, Steve. That was great. So we're going to show you a demo now. This is a pre-recorded video. It'd be quite dangerous to try and do it live. These things can be somewhat unpredictable sometimes. But if your company blocks YouTube, please be aware that you may not be able to watch the video live as it uses a YouTube API. We can, on request, share the recording of this whole event today. So if you aren't able to watch now, just get in touch. The contact details will be shown at the end, and we'll make sure you do get a copy of the demo video. Okay, with no further ado, I'll put the video on now. In this demo, we will show you how Rapita's CAS 32A compliance solution can be used to provide evidence that multi-core timing objectives have been met according to CAS 32A and AMC 20193 guidance. Specifically, we will demonstrate the impact of a common real-world interference channel, the L2 cache. We will look at real results obtained from the Curtiss-Wright V3152 single board computer. This single board computer features an NXP T2080 processor. In this example, the application under analysis is a multi-core matrix multiplication application. On the T2080 multi-core processor, 4 cores access a single L2 cache. It is suspected that competition for this cache may cause interference. The tool automation workflow includes 4 stages: creating a test harness, running tests and collecting test results, analyzing results, and finally exporting results. The first stage is to create a test harness that can run tests to investigate interference effects on the multi-core platform. RapiDaemons support this by applying configurable degrees of contention on specific shared hardware resources by applying high traffic on them. In this case, the cache. This allows tests to be run that measure the impact of interference on multi-core timing behavior. RapiTime and RapiTask instrument the multi-core software so that timing metrics, values from performance monitoring counters on the hardware, and task-level scheduling metrics can be collected during tests. RapiTest turns input tests, RapiDaemons, and instrumented code into a test harness that can be run to collect results. Tests specify the core on which the application is running, the behavior of the test, including the metrics to be collected, and the configuration of RapiDaemons needed to run the test. In our demo application, we will collect execution time metrics and two different values from performance monitoring counters, CPU cycles and L2 cache misses. These values will help us demonstrate any interference that is present and validate our comparisons. To test the impact of L2 cache contention on worst-case execution time in our demo, we write a set of test scenarios, a control where our application is running on one core, and 3 tests where our RapiDaemon is running on 1, 2, or 3 other cores. Our application is running on core 0 in each case. The next stage in the workflow is running the tests on target to collect results. Tests can be run on target from within the RVS user interface, or they can be run separately and results later imported into RVS. RapiTime lets you merge results you collect from different test runs. This helps if you want to collect results in parallel on multiple instances of your platform, supports testing on platforms with limited data collection capabilities, and lets you merge results from different tests so you can access all of your results from a single report. In our demo, we collect our results in 2 batches, which we merge to produce a final report. After you run multi-core tests, RVS makes it easy to analyze your results. RapiTime presents multi-core timing results and values from performance monitoring counters observed during tests. You can compare results from different tests to easily identify the impact of interference in multi-core timing behavior. Comparing results against a control is a convenient way to analyze results. Our results show that our demo application is sensitive to resource contention on the L2 cache. When compared to a control with no RapiDaemons running, tests run with a RapiDaemon targeting the L2 cache running on 1, 2, or 3 other cores increase the software's execution time by a maximum of 20%. The L2 cache hits metric is measured globally and shows the increased activity with the RapiDaemons present. RapiTask lets you see the task-level scheduling behavior of the application from a high level, making it easy to understand this behavior and locate rare timing events. In this demo, we can see the tasks running on each core throughout test execution. Here we can see 4 test runs with different RapiDaemon configurations. In the first, the worker task, the orange segments, is running on core 0, and there are no RapiDaemons on any of the other cores. In the second, one RapiDaemon, the red segments, is running at the same time as the worker task. In the third, there are 2 RapiDaemons running. And in the fourth, there are 3 RapiDaemons. RapiTask also shows the execution time for each task iteration. Highlighting one of the iterations in each test run, we can see the execution time increase. The final stage of the workflow is exporting results so they can be submitted for certification. RVS lets you create custom multi-core testing reports that capture the evidence you need for certification. You can select the text and results that you want to include in the report by generating a template file and using an API to the RVS results. For the demo, we generate a custom report that links to our requirement, describes our test scenarios, and includes the results we collected during the tests. Let's get down to some questions. So I've got one from Sphere here. It's for Gregory, and it's, what are the criteria for operating system selection following the hardware selection?
Wow, that's a good question. Well, it comes down to many things, actually. So, what does the operating system have mechanisms to manage multi-core, for example, virtualization? And do they provide sufficient information that you understand how they're addressing the concerns so that you can explain it to your cert authority? Understanding what the operating system vulnerabilities are and what that means for your application's use. They don't all need to be addressed, but you need to understand what the vulnerabilities are, and each operating system is different. And then also, what support do they offer for tools like the Rapita tools that we talk about here today? Do they provide the metric gathering APIs that make it easy for tools to do the analysis to prove your models? And you can even short circuit that and just talk to Rapita to find out which operating system companies they've worked with, and they'll tell you. So it's a number of things. That was just a quick high-level summary. Thank you.
Thank you, Gregory. Yes, and I will just mention our solution is agnostic to all RTOS providers. So we can't necessarily help you nail it down there, but we can support whatever you do choose. So that's the positive angle there. Thank you very much, Gregory. I've got a question for Altaf here. Why does pure SMP fail to efficiently leverage multi-core processing potential?
So it's really, again, down to, what the application is that's really running on the multi-core processor, right? And what resources it requires to actually execute that operation. So software typically, if it's designed for a single core operation, you try to run that as an SMP application across multiple cores. We just have not seen that performance scale like it should on a, from a single core to a clock, speed scaling capability. But it's application dependent. You can't say that for all the applications. What we have seen is from the work that we've done with different applications that, yeah, there are some cases where SMP might give you good performance, but not in general for all applications. So having hardware affinity and taking advantage of the hardware architecture really is what gives you the best optimization from a performance perspective.
Thank you very much, Altaf. Now one here for Stephen. From David, using the Rapita tool suite, after target hardware is functional, how long does the testing and verification take to achieve DALE level certification? Are we talking weeks, months, years?
My first answer is it depends, of course. It's not weeks, it's months or even years. It depends on how many interference channels are actually active. Any DO-178 verification project, is going to be extensive. When you add on multi-core, that definitely is a further complexity. So yeah, if I have to pick a unit, months to years.
Thank you very much, Steve. Yeah, it's a big challenge, isn't it? Another one to Steve, while we've got you there. This is a challenging one. How do you know when you have uncovered and identified all the indirect and unknown sources of interference? What metric confirms you've completed the on-target analysis such that the certification authorities will accept your analysis results? That's from Kent.
Yeah, really excellent question. So there's no automated way to do this. In the end, it really is engineering judgment. There's no way to mathematically prove that you found them all. So the approach is to show that you've used all available documentation, including what might be proprietary information. So for example, we're a member of the MCFA, so we're getting that certification package information from NXP, and you've analyzed all of that for all potential shared resources. Then you also, depending on the end system system level tests, you need to have testing in place that's thoroughly exercising all of your code with very high coverage, and so with that set of tests, we now go and look for interference against our rapid demons, knowing that those tests are exercising all of the relevant parts of the system. If you then see that you can measure the interference with metrics, observe that it may produce effects on timing, but those are manageable, and you've investigated any anomalies, at that point then you're depending on the engineering judgment that you have found all those that are reasonable to find. Does that mean that there might not be some hidden aspect somewhere? No, you can't prove that you've eliminated the unknown. So what the cert authority is going to look for is that experts have done a reasonable job, provide high confidence that you've identified and measured that all the interference channels are mitigated.
Thank you very much, Steve. One for Altaf. I think this is best directed to you. Some board architectures make use of FPGAs/system on chip with ARM to make the software modular. Not sure in terms of certification of this, but can you explain any pros or cons with that method versus pure multi-core?
Yeah, I mean, FPGA can give you some hardware partitioning in terms of resources, right? So that can be fixed in hardware from a logic perspective that a multi-core processor might not be able to do in that way. So there are some potential advantages there. So there's many different configurations that you could have with that. In a multi-core processor, I think Gregory and also Steve also mentioned, we provide ways to configure the chip so that you can basically minimize the number of interfering channels, right? So, priority, in terms of, what resources are being shared and how you access those resources. So it's down to configurations and what you're trying to achieve with your application, and what configurations can be used is the key to, reducing the number of interfering channels there in the multi-core processor. We try to provide all the hooks that we can to reduce that as much as possible, without adding, additional cost and, silicon real estate to do that. Right? I think you're on mute, Nick.
Thank you very much, Altaf. I think that's been the phrase of the last year or so, and I'm as guilty as anyone else for occasionally missing that. We're 5 minutes over. I'm going to propose we carry on for another 5 minutes and try and answer a couple more questions. We have had an awful lot. Sorry if we haven't got to yours. Contact details are available on the current slide you can see if you do want to get in touch and ask any questions to the panelists that haven't been answered. I'm sure the panelists will also have a look through some of the questions and address them with people who've asked afterwards. So the conversation doesn't end here, but if we can maybe get through a couple more questions and then we'll finish up. So next, I've got one for Greg, which is, it features both NXP and Curtiss-Wright in the question, but I'll point it at Greg. Does NXP provide fault rates for cores to fail, which you would need for FMEA? Where does this information come from that Curtiss-Wright is using?
Right, for some of the SoCs that Curtiss-Wright uses, like the LX2160A, for example, there is also FMEDA data available from NXP, and we use that to proportion the failure rates to the functional blocks, because that provides the data we need. When we don't have that level of data, we seek the real estate usage of the silicon to the functional blocks. So those are the approaches we generally take and we're successful at doing. I don't know if Altaf can add additional color to that. But.
No, I think I would have basically said the same answer. And typically we try to provide as much detail as we can, on the SoC. So it just depends on what's possible and what we can provide.
Thanks very much, guys. So if we're going to finish up, one last question, and this is from Michelle, and I think it's best answered by Steve. How can we take into account the impact of uncontrollable interference, such as the one produced by GPU data fetching?
Yeah, really good question. So let me break it up in a couple ways. the interference is ultimately caused by one of the cores. So if it is giving off work to another device that it can be, say, a bus master, whether it's a DMA controller or a GPU, you can ultimately tie it to some action that was taken on the core. So in that sense, it is controllable, even if it doesn't look like it's directly controllable. And if you have an entirely independent device out there that's taking action outside of what the cores are doing, you may have to consider that as part of the multi-core problem. And in fact, we have multiple projects going where we are considering a GPU as additional cores. But it depends how you're using the GPU. If it's as a co-processor under the control of the general purpose cores, then you might be able to consider it that way. So yeah, excellent question. And you have to get into the details of the particular system to decide how to handle that.